Hello, our new topic is transverse shear. Now, we have seen, we begin with the topic axial loading, then we continue with the torsion. In fact, the torsion generates shear deformation, and then we see bending of the beams or structural elements. Now, let's see what if we have transverse force. Let's consider a beam, simply supported beam. And in fact, we will choose a coordinate system, and let's say that we choose a coordinate system which is attached to its centroid, and y is the vertical coordinate. We may have different types of loading, in fact, so we may have some distributed load. So this is basically W of x. In fact, we may have some bending moments at arbitrary locations, let's say M1, and in fact M2. Moreover, we may have point loads. Now, when we have such kind of a structure, certainly we have forces perpendicular to the structure. Indeed, these forces will tend to, we can say that, cut the structure. Now, we know how it is bended, but in fact, this perpendicular force will try to cause a failure in this structure, and we will see how we can calculate the stress distribution due to these forces. So these forces will try to shear the cross section, so there will be, it is basically a shear, and for this purpose we will just focus to an arbitrary location, let's say that x, and indeed at this arbitrary location we will just take a tiny slice dx. Okay, now let's focus on this tiny slice. Now, we may have an arbitrary cross section. So this is the cross section of the beam, and we have certainly the thin slice, and in fact for this thin slice, we have a neutral axis, and let's say that this is where the neutral axis is located. So remember that neutral axis is the axis on which the stress is 0. Now this tiny piece have a thickness of dx. And I want to calculate the shear stress. So remember that x is located at fixed to the neutral axis, and it's aligned, and therefore I want to determine the shear stress at a distance of y prime. Now the area above, so here the width of the cross section at this particular location y prime is t, and now we have an area. So we made a cut, and in fact this is y prime, and center of gravity of the area above this cut is y prime bar, and the thickness of t. Okay, so this is the cross section. So we are interested in this location which has a thickness of t and has a distance of y prime from the centroid. Now let's look at this piece from the side. So let's draw the stress distribution first of all. So we have a thin slice, in fact we have the neutral axis, moreover we have the bending stresses, and let's say that it's compressive above the neutral axis and it is tensile low, and in fact on the other side there is also a stress, so again it is tensile below the neutral axis and compressive above it. So we have a force couple, let's say that, so we have the bending moment m plus dm, so therefore the moment on either side of the slide may not be equal, m plus dm, and it is m on the left hand side. Certainly there will be a force couple So the resultant force is dF prime which generates this moment, and dF double prime here, and in fact it is dF double prime. Now remember that we are interested in a particular location away from the centroid, and this has a distance of y prime. So let's draw this thin slice again. Now I will just draw the forces above this, or stresses above this location. So this is y prime, and these are the stresses. And let's say that this is on one side, this is sigma 2 prime, and this is sigma prime, and in fact at this cross section I have the shear stress tau at the interface, because this shearing force will certainly try to cut. So remember that this shear force will be balanced by the force here. So there will be a shear stress here, and there will be shear stress here, there will be another shear stress here. So let's assume that we have a shear stress on this face, and on either of the face the magnitude of the shear stresses are the same. Now let's write the force equilibrium for this configuration. So let me repeat once more. Now I'm just interested in the shear stress at this location, so which has a distance of y prime from the neutral axis. Certainly the shear stress at this point is tau, and I have the shear stresses, bending stresses, not the bending, sorry, normal stresses due to the bending, and this is sigma 2 prime on one side and sigma prime on the other side. So this is in fact I will write the moment equilibrium for this particular location. Now sum of the forces in x direction has to be equal to 0. Therefore I can write the forces. So first I will write these forces. So here the stress at particular location, because all of these forces has to be equilibrated. So sum of the forces has to be equilibrated. M multiplied by I is the bending moment of inertia, divided by y prime. Y prime is the distance from the neutral axis. Sorry, and I will sorry, this is not y prime, this is y. Okay, mi y dA prime minus, so this is the stress, this is sigma 2 prime, minus m plus dm divided by I is the bending moment of inertia of the beam, cross section of the beam at that particular location, multiplied by y, integrated over dA prime, and then force generated by this tau, so plus tau, there the width of the cross section is t, so this area on which the shear stress is acting, this area on which the shear stress is acting is T multiplied by dx, so T dx, and this is equal to 0. Now this is our expression. Further, it can simplify. Because m I y dA prime mi will cancel each other, and of course, since the other side of the expression is equal to 0, I can multiply the whole equation with 0. Then we will have dm divided by I, integration over I prime, multiplied by y dA prime is equal to tau T dx. So from here I can get the expression for the shear stress. So the shear stress is equal to 1 over I multiplied by T. T is constant for that particular location. dm dx integration over I prime y dA prime. Now we have something new. This integral, we call this Q. in fact this is the first moment of the area. So certainly the shear stress is then Q I T dm dx. Now we know that derivative of moment, bending moment with respect to x, gives us the shear force at that particular location. So we can write it like this. So VQ I multiplied by T. Now the point is how we can calculate this Q. This is something new for us. Because it might be a little bit challenging for complicated cross sections. So let's write the Q again. In fact, this is the first moment of the area. We can consider it like this. So area as a distributed load. So this is a very small element. So let me draw the arbitrary area, and let's how we can find the Q. Let's just take a small piece which has, let's say, dA prime. So we can consider it as if it's a distributed load acting on this area, and therefore remember that so the moment of the distributed load is equal to the moment of the resultant, has to be equal to the moment of the resultant force, and therefore we can easily say that first moment of the area is equal to the first moment of the moment of the total area, and we can say that that is just located at the centroid of that area, and we call this centroid as y prime bar, and as a result we can say that this is equal to y prime bar multiplied by the a prime. So area multiplied by it is distance to the neutral axis, the distance of the centroid to the neutral axis. How we can calculate the y prime? So again we can say that we can find it. So y prime bar is equal to y dA prime divided by A prime, the area of this particular cross section. Now basically this means that at a particular location the shear stress is uniform. So what it means, so in fact this is, let's consider a rectangular cross section. Therefore I see the shear distribution something like this. So this means that the x is towards us and we have the y-axis upwards, and in fact at a particular location what we see is normally the shear distribution in real is something like this. So we have much higher shear stresses towards the edges, and in fact we calculate the average shear stress at a particular location. So basically, if you have a thinner one, so this is the error that you make. In fact, so this region is the error that you make in calculating the shear stress. But if you have much thinner one, then this will be your shear stress distribution at a particular location. So let's say that this is y prime and this is the error then compared to the average value. Moreover, the second thing is, if you have a highly curved structure, that will be much more clear perhaps. Let's say that this is your cross section, and in fact at a particular location we assume uniform shear distribution, right? But in fact in real, at this particular location, the shear stress is something like this. So this basically means that if you have a very thin structure, this theoretical prediction is losing its accuracy, and moreover, if you have a highly curved structures, again you have error in calculating the stress. Okay, so we have a new definition, in fact, so something new, which is called shear flow. So what's shear flow? We generally make the cross section by different members. So just consider a beam like this, and it goes like this. So just think that this is a tiny slice of the beam, and in fact on either side we have the bending moments. So neutral axis is somewhere here, so we have m dm, and in fact we have on the other side we have m as a bending moment. Now each member or let's say sub-region of this cross section basically carries some amount of load. and we use something called shear flow in order to describe it. In fact, I have the thickness is, so it is dx. So I'm just taking the small portion of the beam and just write the bending moments around it. And in fact, what I'm going to do is I will just look how the reinforcing members, for example, these members will increase the stiffness, and reinforcing members transmit the force, because these may be linked by a rivet, glue, or whatever it is. Let's just take one member and let's look at the problem from the side view. In fact, we have this small member carries, so this is where it is fixed. In fact, this is this area. So we have a force coming to here, F plus dF due to the bending. This is the total force carried by this member, and we have F, and moreover we have dF, which is solely transmitted by this area. And let's say that this distance is T. Okay, so somehow from this region it's glued, it is welded, so whatever it is. Let's write the force equilibrium for this part. In fact, when we write the force equilibrium, what we are going to see is dF is equal to dm I y dA prime. So dA prime is the area here. This is A prime, this area. So this is y dA prime. This is the area that this cross section. Okay, so this is our expression. I can divide the whole equation with dx. Then this is what I'm going to have. dF dx is equal to 1 over I dm dx y dA prime is the moment of this area, so it is Q. And dm dx is in fact V. So we can write this V Q multiplied by I. So this is basically force per unit length, and we call this Q as shear flow. This is basically the one of the measures that we use in calculating the force transmission through members. In fact, again, we can write the Q as y bar multiplied by A prime. So y bar is the centroid of this area to the natural axis. Distance of centroid to the natural axis. Now let's begin analyzing by a simple cross-section for the shear problems, transverse shear problems. Assume that we have a very simple rectangular cross-section, beam with a rectangular cross-section. The width of the rectangle is B and height is given as H. And let us derive the expression for a location, so the stress at an arbitrary location. In fact, since we have the rectangle, natural axis is just located at the center. So distance to the bottom line is H divided by 2. So let me draw this rectangle once more. So this is our cross section. This is where natural axis is located, and we want to determine the stress at y. So this distance is h over 2. This is our area above the point of interest, and this is B. Okay. Now, first thing is, for this cross section, we will determine the bending moment of inertia. Bending moment of inertia for this cross section is 1 over 12 B h cube. So this is the bending moment of inertia around natural axis. And next thing is to find the Q for this area. Now, the centroid of this area is located at y prime bar. So y prime bar is, if this distance is y, this distance is h divided by 2 minus y. So h divided by 2 minus y divided by 2, and we will subtract this expression from h divided by 2. So let's write it in explicit form. So y prime is basically h divided by 2 minus this distance. That distance is h divided by 2 minus y divided by 2. And then we need to calculate the area. This is our area. A prime is equal to then B multiplied by H divided by 2 minus Y. So this is our expression. If you simplify, if you calculate the Q value from here, Q is Y prime bar multiplied by A prime bar, and if you do the calculation, what you are going to get is 1 over 2 H square divided by 4 minus Y square multiplied by B. This is our Q value. Again, 1 over 2 H square divided by 4 minus Y square multiplied by B. So this is the multiplication of Y prime bar multiplied by the A prime. Now we can write the stress. So stress at this particular location is V, is the shear force, multiplied by Q multiplied by I multiplied by T. T at that particular location is B, so this is V multiplied by Q. Q is 1 over 2 H square divided by 2 minus Y square multiplied by B. Divided by 1 over 12 B H cube multiplied by B. Now this expression can simplify to (6V) divided by BH cube multiplied by H square divided by 4 minus Y square. So it is 6 times the shear force BH cube in parentheses H square divided by 4 minus Y square. So when Y is equal to H over 2 or minus H over 2, as you see from the expression, automatically the shear stress is 0. So there's a parabolic distribution of the shear stress, and shear stress is maximum when Y is equal to 0. So we can calculate, we can substitute 0 to here in order to find the maximum shear stress. So maximum shear stress is equal to (6 BH cube V multiplied by H square divided by 4, and this is equal to 1.5 multiplied by V divided by B multiplied by H. Or in other words, this is 1.5 V divided by area, and this is nothing more than, so V divided by A is the average stress, so it is 1.5 tau average. Sometimes for arbitrary cross sections it's possible to define formulate the expression for the maximum stress, because generally we are interested in maximum stress, and that is the threshold for failure, in fact, in many problems. So we write the maximum shear stress formula as tau K multiplied by V divided by area, and K for rectangle is 1.5. So K is the shear factor. For different cross sections you can calculate the different K values, and you can easily calculate the maximum shear stress without making without calculating the first moment of area and all other things. Okay, we will begin with our first problem in this chapter. It is 7.1. If the wide flange beam is subjected to a shear of V is equal to 20 kilonewtons, determine the shear stress on the web at A. Indicate the shear stress components on a volume element located at this point. So we have a flange, an I-beam. The width of the flange is given as 200 millimeters, and it has a thickness of 20 millimeters here. Of course, we have the web. Web has a thickness of 20 millimeters as well, and the distances between the two flanges is 300 millimeters. So we are asked for the shear stress at point A. Okay, now first let's draw the cross section and let us define the variables. Okay, this is our I-beam. Let's say that this width is B, this is T, this distance is H. I-beam is symmetric in both axes, both horizontal and vertical axis. And so we don't need to define any other dimension. Moreover, the web has a width of T as well, and this is where A is located. So these are our dimensions. Let's write the variables. H is equal to 0.3 meters, T is equal to 20 millimeters, which makes 0.02 meters, and B is equal to, again, 200 millimeters, which is 0.2 meters. So these are our variables. Now let's write the we need to calculate the moment, bending moment of inertia, and in fact we need to calculate the moment of the area. Moreover, we don't need to calculate the centroid or the position of the neutral axis. Since the beam is symmetric, we can already say that neutral axis is just at the center of the cross section. Therefore, we don't need to calculate it. In fact, we are asked for the shear stress. Moreover, we need to calculate the area above this point, first moment of the area, and this is, let's say, A prime. This area has a centroid, of course, which can be defined as Y prime bar. Okay, so now let's begin by calculating the bending moment of inertia first. Now we have two flanges and one web. So the bending moment of inertia is, for the two flanges we have 2 multiplied by 1/12. So it has a width of B, thickness of T cube. So this is with respect to its centroid of this area. Now we need to shift it to the neutral axis. The area is B multiplied by T, and distance to the neutral axis is H divided by 2 plus T divided by 2. Let's continue below. So I continue the equation here. I will continue the equation here, and now I will write the moment of inertia of the web at the center. It is 1/12 T multiplied by H cube. If you put the values, what you are going to get is 0.2501, 10 to the power -3 meter to the power 4. So this is the bending moment of inertia. Now let's calculate the first moment of the area with respect to the neutral axis. So let's say that first moment of the area for the point A is, so moment of this area, in fact it is nothing more than distance of its centroid to the neutral axis multiplied by its area. Natural axis is y prime is located at h divided by 2 plus t divided by 2. Area of it is b multiplied by t, and the value that you are going to get is 0.64. If you put the values into their places, it's 0.64 10 to the power minus 3 meter to the cube is the unit. Now we can calculate the shear at point A. So it is B multiplied by QA, first moment of the area. Now we are asked for the shear stress on the web, and the thickness of the web is T. Multiplied by bending moment of inertia. Now let's put the values. V is 20 kilonewtons. It is 20 10 to the power 3. Q is 0.64 10 to the power minus 3. Divided by thickness is 0.02, and bending moment of inertia is 0.2501 10 to the power minus 3. Now from here we can calculate the shear stress at A as 2.56 megapascals. Now let's draw the shear stress on the volume element. I will draw it from the side. So this is our volume element. So remember that the direction of the shear force is like this. Therefore it is the direction of the shear stresses at point A is like this. So this is the front face of the cross section. Okay. Our problem is 7.5. If the T-beam is subjected to a vertical shear of 60 kilonewtons, determine the vertical shear force resisted by the flange. So we are asked for the total force resisted by this flange, so not the web of the T-beam. The dimensions are given, the force is given. So let's first draw the cross section of the beam and then define the variables. So this is our flange. Now, in fact, it's not symmetric with respect to the horizontal axis. Therefore, we need to find the position of the neutral axis. This is what we need to do. This is our neutral axis. So let's say that this distance is h1, and we have this distance. Let's say that this is h2, and certainly the next thing that we need to do is to define the width. So this total distance as b. Okay. Now, again, we need to find out the location of the centroid. So this axis, I will choose the bottom line of the cross section as my reference point. Therefore, this distance is y bar. In fact, y bar is equal to sum of the moments of the areas divided by the total area of the cross section. I have two areas. One is the web and the second one is the flange. So let's write it. The web has a centroid at location of h1 divided by 2. Sorry, let's write it here. That's clear. It will be much more better maybe. So h1 divided by 2 multiplied by the area. Area is b divided by 3 multiplied by h1. And next is the area of the flange, this part. So area of the flange, the centroid of the flange is located at h1 plus h2 divided by 2 multiplied by its area. Area is b multiplied by h2. And now the total area is b divided by 3 multiplied by h1 plus b multiplied by h2. Now let's I forgot to write the variables. Let's write the variables here. So then we will put it into the expression. H1 is 0.15 meters. H2 is 0.075 meters, and B is 0.3. Now we can substitute the variables into their places. Then what we are going to get is, for the location of the centroid, 142.5 millimeters. Okay, now we need to calculate the bending moment of inertia with respect to the neutral axis. This will be our next step. First, this part, the web of the cross section, it is 1/12. The width is b divided by 3 multiplied by h1 cube. Then we will shift it to the neutral axis. Area is b divided by 3 multiplied by h1 multiplied by y bar minus h1 divided by 2 square. So distance to the square of the distance to the centroid. I will continue below. Plus, now moment of inertia of the flange it is 1/12 b h2 cube plus area of the flange, because we will shift the moment of inertia to the neutral axis, b multiplied by h2. Center of this flange is h1 plus h2 divided by 2. h1 plus h2 divided by 2. Okay, so this is the moment of inertia with respect to its centroid, and then we are shifting it to the neutral axis minus y bar square. If you put the values into their places, what you are going to get is 152.578 meter to the power 4. Now we are asked for the shear force carried by the flange of the beam. So this part. in order to make it clear, let me draw the cross section again. So this is our reference point. Our natural axis is here. Now we just take an arbitrary point. Okay. On the flange. On the flange. So and let's say that this is y. This distance is y. Now we need to calculate the q for this area, and y can change in fact. So certainly this area has a centroid y prime bar, and this is I prime. Now let's write the q value. Q is a function of y. In fact, it is equal to y prime bar multiplied by a bar. Now let's write the y prime bar. Y prime bar is equal to h1 plus h2 plus minus y, so this distance, divided by 2, it's half of it, plus y. And y prime bar is certainly distance to the centroid. Because we always we calculate the moment of the area with respect to the centroid always. So minus y bar. Okay, so this is y prime. Let's calculate the area. A prime is then h1 plus h2 minus y multiplied by, so this is the thickness, multiplied by b. This is the area. Now we can write the q, first moment of the area, as a function of y. So centroid is h1 plus h2. So it will simplify because I have y minus y divided by 2 and plus y. It will make y divided by 2 minus y prime, y bar, multiplied by the area, that is h1 plus h2 minus y multiplied by b. Now I have the q value as a function of y. Now what I'm going to do next is I will write the shear stress. I can write the shear stress as a function of y. Tau as a function of y on the web is, remember that v q as a function of y. Bending moment of inertia is constant, I and I. So bending moment of inertia with respect to the neutral axis multiplied by the width of the flange, it's b. So if you put all the values, what you are going to get is minus 1.9066 10 to the power 8 multiplied by minus 0.225 plus y multiplied by y minus 0.06, and all the distances are in meters. Now we are asked for the force carried by the, let me repeat it again. So shear force is a function of y, and in our expression only the first moment of the area is function of y. So we have the shear force coming to the flange. It's given as 60 kilonewtons in the question. Then it will be divided by bending moment of inertia multiplied by, since we are interested in the flange, force carried by the flange. In fact, the thickness of the width of the flange is b, the width of the cross section on the flange is b. Then we are left with this function. We arrive at this function as a function of y, for the shear stress. It is minus 1.966 10 to the power 8 multiplied by minus 0.225 plus y multiplied by y minus 0.06. So this is the function for the shear stress. Now let's calculate the force, shear force carried by the flange. The flange, shear force carried by the flange is sum of the stresses. In fact, flange y varies from h1 to h1 plus h2. So stress multiplied by the area, area there is B multiplied by so I just take a very thin slice and write the force there. Therefore it is B multiplied by dy if you do the integration, what you are going to get is 19,000 or 19,078.3 newtons. So this is the total force carried by the flash. Okay, hello. Our problem is 7.6. So let's read the question first. The wood beam has an allowable shear stress of 7 megapascals. Determine the maximum shear force V that can be applied to the cross section. So we have a beam made of wood, and in fact it has an hollow cross section. There now the allowable stress, so the strength value is given to us, and we are asked for the maximum shear force that can be applied to the structure. And therefore so let's remember the formula for the shear stress. In fact, so that's the first step that we need to do maybe in order to solve the problem. So shear stress at arbitrary location is Q multiplied by bending moment of inertia multiplied by the thickness at a specified cross section. Now here in this equation only Q is function of the distance to the neutral axis, and certainly this is the first moment of area, and in fact the shear stress will be maximum where first moment, so this ratio basically is maximum. So when this ratio is maximum, certainly the shear stress will be maximum since the shear force is maximum. Let's return back to our cross section then, after making this statement. We have a square cross section. This is neutral axis, and let's say that this distance is A and this is T. Now we will begin by calculating the bending moment of inertia. So in order to do this, first I will calculate the bending moment of inertia of the whole square. Then I will subtract the bending moment of inertia of this hollow part. In fact, the neutral axis is at the center. Since the cross section is symmetric, we don't need to calculate the location of the neutral axis. So I is equal to 1 over 12. Now the width is equal to the height for this problem. So it is a to the power 4 minus 1 over 12. This distance is a minus 2t to the power 4. Now this, if we put the values into their places, we are going to get 1.25 10 to the power minus 4 meter to the power 4. Now let's calculate the Q. In fact, now we can easily say that the width is minimum here, and in fact the moment of the area is also maximum on the neutral axis for this cross section, because the area is getting larger. So we can write the maximum first moment of the area as sum of the moments of the areas. Now let's return back to the cross section again. We can easily divide the cross section above the neutral axis into 3 parts: 1 rectangular horizontal part and 2 small square part. In fact, neutral axis of this centroid of this is located as at, this is t divided by 2, in fact, because this distance is t in fact, and this is located at this is a divided by 2 minus t divided by 2. So this is a divided by 2 and this distance is t divided by 2. So we can write the first moments of the areas. So we have 2 small squares. Their area is this is a divided by 4 multiplied by t. So this is t, this is a divided by 4, and this distance is a divided by 8 or t divided by 2. Plus moment of the large area here, that is a multiplied by t, that's the area, and position of the centroid with respect to the neutral axis is a divided by 2 minus t divided by 2. If you put the values, what you are going to get is 8.75 10 to the power minus 4 meter to the power cube, not 4. Okay, so this is the first moment of the area at the position where we have the maximum stress. Now let's write the maximum stress formula. In fact, allowable stress has to be equal to shear force multiplied by Qmax divided by bending moment of inertia multiplied by the thickness there, the width of the cross section, that is 2t in this case. From here we can calculate the V. V is equal to tau allowable multiplied by I multiplied by 2t divided by Qmax. If you put the values into their places, so maximum shear force that can be carried by this beam is 100 kilonewtons. We will continue with question 7.12. Question is like this: the beam has a rectangular cross section and is made of wood having an allowable shear stress of 1.4 megapascals. Determine the maximum shear force V that can be developed in the cross section of the beam. Also plot the shear stress variation over the cross section. So we have a rectangular beam. The height is 300 millimeters, width is 200 millimeters, and we are asked for the maximum value of the V, since the allowable shear stress is given to us. Okay, so what we are going to do is first we will calculate the moment of the area. In fact, as a function of the coordinate. So this is our rectangle. It has a width of B and height of H. Natural axis is just at the center and it has a distance of H divided by 2. So let's define the variables. H is 0.2 meters and width B is 0.2 meters. I will just choose an arbitrary distance y, and I will calculate the moment of area I will calculate the shear for this location, and in fact I will calculate the moment of area for this. So let's calculate the moment of area first moment of area for this particular location. Now this is my distance y. Certainly this distance is the height of this small rectangle is h divided by 2 minus y, and as a result the center is located at h divided by 2 minus y divided by 2. Then I will sum it up with the y. So the centroid is located at h divided by 2 minus y divided by 2 plus y. This is the location of the centroid, and area is h divided by 2 So this is the centroid. H divided by 2 minus y divided by 2 plus y is the location of the centroid from the neutral axis, and the width of the shaded area is h divided by 2 minus y, and then we will multiply it by b. Okay, if we put the values, what we are going to get is 0.1 multiplied by y minus 0.15 square meter to the power cube. Now this is first moment of the area. Now we will calculate the bending moment of inertia with respect to the neutral axis. It is 1 over 12 b h cube, and the value that you will get is 4.5 10 to the power minus 4 meter to the power 4. Okay, now we know that the formula for the shear stress is tau is equal to V is the shear force multiplied by the first moment of area divided by bending moment of inertia multiplied by the width at that location. So it is B for us. Now we know that the shear stress cannot exceed, so the maximum shear stress cannot exceed the allowable stress. So from here we can write that shear force is equal to tau allowable multiplied by bending moment of inertia multiplied by width of the cross section divided by Q, and in fact Q is a function of Y. Okay, now if we put the values into its places, what we are going to get is This is TL oval. I and I multiplied by B sorry. I'm just writing the equation again. So let's go down. Okay. So it is TL oval. Well, we simplify the equation. It is 2B H cube divided by 3 H minus 2Y square. So TL oval is constant. It is given to us. It is 1.4 megapascals, and B is known, H is known, and it is function of Y. Certainly, this expression becomes maximum when Y is equal to 0. So when you substitute 0 to Y, what you are going to get is (56 kilonewtons). So basically, we know that the shear stress is maximum at the center. So the moment of the area is maximum. In fact, we can draw the distribution. If you draw the shear distribution along the or through the cross section, so this is tau, this is Y, and it's going to be something like this, and at the center it is TL oval. So this is the stress distribution, and this is minus H divided by 2, and this is H divided by 2. Okay, now our question is 7.15. The strut is subjected to a vertical shear of 130 kilonewtons. Plot the intensity of the shear stress distribution acting over the cross-sectional area and compute the resultant shear force developed in the vertical segment AV. So we have a plus-like cross-section, as you see, and there is a shear force of 130 kilonewtons. First, we are asked for the stress distribution. So remember that through the width of the cross section, we assume that the shear stress is constant, and then we are asked for the force carried by this segment from A to B. Okay, so we will first begin by defining the variables. In fact, it is better to draw the cross section once more, maybe. So this is our cross section. It is symmetric in both vertical and horizontal axis. Therefore, we can say that neutral axis is located just at the center, and we can put our reference point to the neutral axis. So this distance is, let's say, h, and we have this distance as t. So h is equal to 0.15 meters and t is equal to 0.05 meters. Okay. Now first we are going, I will calculate the moment of inertia. In fact, with respect to the neutral axis. Now we can divide the whole cross section into three parts. So one vertical rectangular part which is at the center, and two rectangular parts on either side, on both sides. So the moment of inertia of this rectangular part is 1/12. The width is t, and height is 2h plus t to the power cube plus so this is the moment of inertia of the central part. So 1/12 t multiplied by 2h plus t to the power cube plus I have two rectangular parts on either side, one here and one here. So it is 2 multiplied by 1/12 and the width is h and the height is t cube. So if you put the values, it is 1/12, t is 0.05, 2 multiplied by 0.15 plus 0.05 to the cube plus 2 1/12, h is 0.15 and t is 0.05 to the cube. And the result is 1.81 10 to the power minus 4 meter to the power 4. Okay, now this is our moment of inertia. Now we need to calculate the moment of the area. Let's return back to our cross section. Now, if you look at this cross section, we certainly see that there are two different regions. So one is above the point A, and one is below the point A to the natural axis. So there are two regions, and in fact we need to calculate the moment, first moment of the area as a function of y. So what we are going to do is, first I will take an arbitrary location here, and I will calculate the moment of this arbitrarily located area, and I will say that it is Q1, and then I will calculate the moment of area above the neutral axis, which is Q2. And both will be function of y, in fact. So let's begin by calculating Q1, which is a function of y. Now, certainly the centroid of this area is h minus y divided by 2 plus y. This will be the centroid, not h minus y, h plus t divided by 2. So it is h plus t over 2 minus y divided by 2. So in fact this is from here to the centroid, and then we add the y here. So this is the centroid. Then we need to calculate the area. Now this distance is h plus t divided by 2 minus y. Multiplied by t. So this is the again, this is the area. So h plus t divided by 2 minus y is the height of that area multiplied by t. So if you put the values, what you are going to get is 7.65, 10 to the power minus 4, minus 0.25 y square. Meter to the cube, meter to the power 3. So this is the expression for Q1. Now we will calculate the Q2. Certainly Q2 is the moment of the first moment of the area above the neutral axis now, but in fact now we just take an arbitrary location between A and the neutral axis. Therefore we need to calculate the moment of this area down to A, first moment of the area. Then we will add the moment of the small rectangle located here. So Q2y is equal to, now the area, the above, it is, the centroid is located at h plus t divided by 2, and the area is t multiplied by h plus, now I will consider the area of the small rectangle here. So it is t divided by 2 minus y divided by 2 plus y that is the location of the centroid with respect to the neutral axis, then the area of it, so it is t divided by 2 minus y multiplied by the width is 2h plus t. So basically 1h here, 1h here, 1h here, and plus t. And what you are going to get is if you put the values 8.6, 10 to the power minus 4 minus 0.175 y square, and the unit is meter to the power cube. So this is, if you look at the expressions again, when y is greater than t over 2 we have q1, and when y is smaller than t over 2 we have q2. So when y is smaller than t over 2 we have q2. Now we find the q as a function of coordinate system. In fact, we are asked for the intensity of the shear stress distribution. Therefore, we are going to have two shear stress distributions. So when y is greater than t over 2, we have T1y. In fact, it is V, the shear force, multiplied by Q1y divided by bending moment of inertia with respect to the neutral axis multiplied by the thickness, and thickness there is T. Now when y is smaller than T over 2, we have T2 y, and then we have V Q2 y divided by I and I multiplied by, now the width there is 2h plus T. So these are the stress distributions. In fact, if you put the values, T1 will be 10.951 10 to the power 6 minus 357.593 10 to the power 6 y square, and the unit is pascals. So T2 is 1.756 10 to the power 6 minus 357.593 10 to the power 6 y square, and the unit is again pascals. So these are the expressions for the stress as a function of y, as a function of coordinate. Now we are asked for the distribution. Now let's say that this is tau. Stress goes like this and then suddenly decreases. In fact, the structure is, the cross section is symmetric, so it is something like this. So this distance is T divided by 2, and this coordinate is h plus T over 2. So this is y. So this is our shear stress distribution. Certainly we see that as a result of change in thickness, there is a strong jump in the shear stress at point A. This is what we see. So if you put the values here, so what you are going to get is, here it is, this value is 10.727 megapascals. In fact, it is 0 here, and the value here is 1.532 megapascals. Moreover, on the neutral axis, the shear stress is 1.75 megapascals. So, and in fact, it is symmetric with respect to the neutral axis. Okay, so these are the this is the distribution of the shear stress. As you see, now we are going to calculate, we are asked for the force carried from in the vertical segment A to B. Now, for this purpose, what we are going to do is we will integrate the stress there. So A is located at T over 2, and B is located at H plus T over 2. And in this region, we are, T1 is acting, now we have a infinitely thin unit area, and there it is T dy. This is the area that the stress is acting. So if you do the integration, what you are going to get is .005 megapascals.